All right, so let's talk about this first class of enzyme inhibitors, so-called competitive inhibitors. Now, as the name kind of implies, you can get a sense of what a competitive inhibitor is going to do. It's going to bind to the same place that the substrate binds and compete with it for binding. So from that alone, you can kind of extrapolate to the kinds of molecules or the features that a competitive inhibitor would have relative to the substrate, right? They're going to be really similar, right? In most cases, you're going to have an inhibitor that shares a lot of the same chemical features, size, charge distributions, groups, whatever, that look an awful lot like either the substrate or the transition state, right? And they're going to bind to the active site and just basically clog it up. By getting in the way, they're going to keep the substrate molecule from binding. And if substrate can't bind, you can't do chemistry, right? So what kind of scheme would that look like? In the context of steady state enzyme kinetics, the way we've been talking about that, what would it look like? Well, let's start back with the Michaelis-Menten scheme. We'd start, of course, with our enzyme plus substrate goes to the Michaelis complex. And just to keep things simple here, I'm going to write down Km, right? And I'm going to assume that for the enzyme that we're thinking about here, that the Michaelis complex is in thermodynamic equilibrium, right? Wouldn't have to do this. In fact, you can explicitly not do it. You get the same answer. But just for simplicity right now, I'm just gonna use the notation that way rather than using K sub S and then switching back. Because again, if you can explicitly use a steady state approximation, Briggs-Haldane, and you'll get to exactly the same endpoint. Okay. So then, of course, we know we have our step of doing chemistry, Kcat, to enzyme plus product. And now we need to layer on top of this binding equilibria for the small molecule that's a competitive inhibitor. And for competitive inhibition, this is pretty easy because it would go right here. And we're going to symbolize that with sub I, this this for the inhibitor molecule. And we're therefore going to presume we have an equilibrium between the free enzyme and the inhibitor to form this EI complex, which of course can't do any chemistry. And we have an associated equilibrium constant here, which we're going to give the symbol K sub I, right? So that's the equilibrium constant for binding of the inhibitor to the enzyme. And now the question becomes, what does that do to the observed enzymatic steady state enzyme kinetics? If you look at the initial rate in the presence of the inhibitor, what happens to it? B, can we quantify it? C, can we use that to get a sense for how good a given inhibitor is, or more specifically, can we use steady state enzyme kinetics to measure Ki? Because if we can then compare different inhibitors or different conditions for a given inhibitor, right? That's the goal. All right. So to do that, we're going to start back where we have often started with these expressions. We're going to use a sort of set of expressions we know we can set up. So for the Km, right? Again, remember we're thinking about this as an equilibrium constant, right? Again, wouldn't have to, but it's just going to simplify our life a little bit right now. So we can define that, right, as this KD-like relationship between the free enzyme, the substrate, and the Michaelis complex. We know we got that guy. We can set up a similar expression, right, for the inhibitor binding constant, right? This would just be, this would just be free enzyme now times the inhibitor concentration divided by concentration of the enzyme inhibitor complex, right? And remember, for these deriving these expressions, we got one more piece of information. Remember, right? It's the concentration of total enzyme, right? Which is just going to be equal to concentration of free enzyme plus the concentration of the Michaelis complex. And now we got one more species, the concentration of the enzyme inhibitor complex, right? Okay, now the trick is just to put this all together, right? So that's not so hard. Multiple different ways you could do it. We're going to start out by first, what we're going to do is we're going to rearrange this expression, and then we're going to go substitution happy. And as we've always done before, we got three different variables here. We're just going to reduce this down to an expression that only has one, right? Okay, so first we're going to go over here and solve this expression for the concentration of the enzyme inhibitor complex. That's pretty easy, right? Concentration of the enzyme inhibitor complex has to just be equal to concentration of free enzyme times the concentration of the inhibitor divided by the equilibrium constant for binding. Okay, that's cool, right? Not such a big deal. Now we're going to take that baby and we're going to substitute that in to this expression for total enzyme, right? Because that's going to help us start getting rid of a variable, right? We'll essentially, we'll have eliminated the variable of the enzyme inhibitor complex and replace that with the definition it's related to for other things, right? Sort of kind of reduce our number of variables, right? So we do that. This expression then becomes free enzyme concentration is now equal to the total enzyme concentration is equal to free enzyme concentration plus concentration of ES plus concentration of free enzyme over the concentration of the inhibitor divided by K sub I, right? Okay, no big deal. Group some terms here, right? Yeah, free enzyme, group some terms, factor out. We can rewrite this expression now as concentration of the enzyme total is simply equal to concentration of ES, right? Plus concentration of free enzyme times 1 plus concentration of the inhibitor concentration divided by K sub I, right? That's pretty cool. Fairly straightforward. Okay. Now we can solve this expression. All right, I'm going to turn around and solve this expression now for free enzyme, because remember the name of the game, remember where we went to before, it's the concentration of the Michaelis complex, right, times Kcat that's going to determine the rate. So the whole idea is to boil this thing back down to an expression in terms of the Michaelis complex with as few other variables as we can possibly come up with, right? All right, so let's solve that expression for the free enzyme concentration. If you do, you now end up with an expression that looks like this. Concentration of free enzyme is simply equal to concentration of enzyme total, right? Minus concentration of the Michaelis complex divided by 1 plus that inhibitor term, concentration of inhibitor divided by K sub I, right? Straightforward. Okay. But we've got another relationship we can work with here. We haven't used it yet. That's our definition of the Km in this case, right? Could have done this with Ks and then substituted, or we could have done this with the formal, like I said, steady state expression. Steady state expression is a little more involved, but like I said, I've said like 3 times now, you end up in the same point. So we're just going to stay with this idea that thinking about Km as an equilibrium constant because it works either way. All right, so okay, so we know we can rearrange that so that the Km, well, let's just write it back out again so you can see it here approximately. Remember, this is concentration of enzyme, concentration of substrate divided by Michaelis concentration. We can rearrange this expression. So we have Km concentration of Michaelis complex equals free enzyme times concentration of substrate. Okay, see where we're headed? Now we got this guy. We can take that guy, substitute in right over here, rewrite that expression now as Km concentration of Michaelis complex equals concentration of substrate times concentration of E total enzyme minus concentration of the Michaelis complex over 1 plus concentration of the inhibitor over K sub I. Now I gotta get 2 more steps, right? And I'm gonna leave this intervening step here to you guys because this is no big deal, right? I sort of pretty well set it up for you here. All we have to do now, right, is solve this expression for ES, right? And then substitute that resulting expression into the thing we wanted to begin with, which is that, remember, the initial rate is just equal to K cat times the concentration of ES. So if you solve this expression here for ES, right, and then substitute that in here, what you'll find is that your expression for the initial rate is simply equal to something that looks really familiar. You come back to this expression of K cat times the total enzyme concentration times the substrate concentration divided by Km times 1 plus the inhibitor concentration divided by K sub I plus concentration of substrate, or written in the way we know how to do it, because we know that's just Vmax. So we can write this out as Vmax concentration of substrate divided by Km times 1 plus concentration of inhibitor over Ki plus concentration of substrate. It's a little sloppy. That ought to look pretty familiar, all right? If you remember, the initial rate expression from before was just equal to Vmax concentration of substrate over Km plus concentration of substrate. Mathematically, the basic form of those two expressions is exactly the same. Exactly the same. The only difference here is that we basically have now modified Km. We basically have a term that we multiply by Km, and it has a really important impact if you look at it, right? You think your concentration of inhibitor, that's going to have some value, right? Greater than 1, or you're not doing an experiment, right? The Ki, presumably, if it binds, it's going to have some value greater than 1. So that whole expression is going to have some value greater than 1, which means the impact of a competitive inhibitor is to increase the Km. And again, if we're thinking about Km, and it doesn't matter necessarily as either a true dissociation constant, or in terms of the sort of more strictly correct half saturation point, if we're thinking Briggs-Haldane, in either case, Km goes up. And if Km goes up, that means the apparent affinity has decreased. It's not substrate's not binding as well, or we need more substrate. We got to put in more substrate to get the enzyme going at two half saturation in the presence of the inhibitor, right? But you also notice something else. What happens to Vmax in the presence of a competitive inhibitor? Nothing. Competitive inhibitors have no impact on the ability of the enzyme to do catalysis. Therefore, Vmax is unaffected. What's affected is the ability of the substrate to load with the substrate, because the competitive inhibitor is basically getting in the way, right? So those things have a distinctive impacts when you look at the consequences on steady state kinetic data when you plot it out, right? So I'm gonna look at this two different ways. All right, we're gonna consider both the classic Michaelis-Menten plot, and we're gonna consider double reciprocal plot, right? So here we got concentration of substrate. Here we've got 1 over the concentration of substrate. And remember, we've got to have that, that sort of, our axis here is offset a bit, right? Because our true zero axis is going to be like right around here, all right? And then on the y-axis here, we have our initial rate. Here, we're going to have 1 over the initial rate, right? Okay, and doing normal steady state enzyme kinetics, right? We have these nice saturation plots. It's going to look a little bit like that. We know this is our Vmax, right? Okay, all is good, right? And this is sort of in the absence of the inhibitor. On our sort of standard double reciprocal Lineweaver-Burke plot, we'd have something, or we better see something that looks like this, nice straight line. That's a little ugly. So let's see how I make it straighter. Okay, that's not bad, right? Again, minus the inhibitor. Remember over here on the Lineweaver-Burke plot, over here, we've got that -1 over the Km point, right? And here we've got the 1 over Vmax spot on that intercept, where this is technically, this is sort of a, I'll put it this way, let me redraw that line. Your data for Lineweaver-Burke plot, of course, is only going to be up here. This is extrapolated back here, right? You guys hopefully remember that that's the case, right? Let me move that over where it's supposed to be. Okay. Okay. So when you extrapolate that plot back, now you get your -1 over the Km, right? Okay. So what happens when you add an inhibitor? And we established that all the effect is in Km, right? Well, what happens is these plots change in a characteristic way. In the case of, I should only indicate one other thing over here. Remember, at our half saturation point here, right, we have our Km, right? Okay, so now what happens when you do this in the presence of inhibitor, right? These curves shift in a characteristic way. Of course, in the standard Michaelis-Menten plot, the curve is going to do something like this, right? So that now, presence of the inhibitor, we see what happens. The Km shifts out here, or I should say, the Km apparent, right, shifts to higher concentration values, right? And in the case of the double reciprocal plot, same thing is going to happen, but that curve is now going to do this, right? Again, this is plus inhibitor. Here we have plus inhibitor, right? And so now over here, our -1 over Km apparent, right? It becomes obvious sort of what's happening, right? All the effect is in the Km, which is why the standard plot, or the Michaelis-Menten sort of direct plot, the curve shifts over to the right, the K apparent shifts to higher concentration, and in the double reciprocal plot, but you'll notice that the Vmax doesn't change, right? So this intercept on this extrapolating axis is exactly the same because the Vmax doesn't change, which also means in a standard plot, if you can shovel in enough substrate, this curve is going to eventually get back up to the Vmax, right? I've tried to draw it so that seems obvious. That becomes very obvious in these double reciprocal plots, which is one of the reasons in enzyme inhibition, these double reciprocal plots still get used a lot because they visually represent what's going on with enzyme inhibition really simply, really cleanly, because a good clean experiment under steady state conditions that's a good competitive inhibitor is going to show a family of curves where this y-intercept is all the same. The x-intercept then moves around as the Km changes, but the Vmax doesn't, right? Okay. So that's great. That would sort of visually confirm that we had a competitive inhibitor. But again, the point here, the goal usually is that you want to know the Ki, right? You want to know how good an inhibitor is this molecule. What's the value of this constant, right? Okay, how do you do that? Now, the way you do it, of course, is the way we've done other experiments or I've talked about other experiments kind of like this before. You do a whole series of experiments, right? You pick a set of conditions where your enzyme is good, right? And then you'd run a whole family of inhibition experiments, right? At different concentrations of inhibitor. right? Where your inhibitor concentration, right, is increasing, right? And you fit that data, right? And out of this data would come a whole family of Km apparents, right? Each one of these guys, right, would give you some different apparent value. You wouldn't do it to the Hass by eyeballing it. That'd be bad, right? You would fit the data, right? Old school method would be to convert the data and get this family of double reciprocal plots, these lines, right, that are doing something like this, right? And get the KMs out of that. Modern era, of course, you would do the actual nonlinear fits, get those apparent KMs out of it. And we know there's a relationship between the apparent KM and the KI. And that relationship is sitting right here, right? If you look at it. That whole expression, right? That is equal to that Km apparent, the way I'm talking about it, right? So making that a little more explicit, from this, we have this sort of Km apparent value, which we know has to be equal to the true Km times 1 plus concentration of the inhibitor divided by Ki, right? Just multiply that through. That means Km plus Km over Ki concentration of I. Y equals mx plus b. It's a line, right? So from a family of experiments done like this at different inhibitor concentrations, one would take those apparent Km values, right, and plot them out as a function of the inhibitor concentration, right? And out of that, you should, if you've done it right, and the enzyme is doing what you think it's doing, you should then get a straight line, right? And the slope of that line, of course, is then the Km over Ki, as shown in this relationship here, right? And if you know the Km, if you know the Km, you can calculate the Ki, right? And determine how good a competitive inhibitor this particular molecule was.